my dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. So today it's our 135th International Physics webinar. So hope you are well and safe from Corona pandemic. So all we know that we are living in a Corona pandemic situation. So we cannot continue our normal academic program inside the campus. So we have to start our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online International Physics webinar. We have successfully completed our 134 International Physics webinar. So we are trying to adjust with this new normal situation. So today I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Department of Physics, University of Tokyo, Japan, in physics. And we have with us here today Dr. Koichi Hamaguchi, Associate Professor, Department of Physics, University of Tokyo, Japan. And he has already connected with us. So I'd like to welcome our speaker, sir. Good afternoon, and welcome to our International Physics webinar, sir. So thanks for accepting our invitation for second time. So I would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology. For those who are connected with us, so I'd like to inform that we have divided our webinar in two parts. First, our speaker will deliver his piece, and at the end we have a discussion session. In that time, anybody can join with us, and you can ask question by commenting. So, sir, you can start your session. It's your time.
Can I start now?
Yeah, you can start, sir.
Okay. Yeah. So thank you very much again for the invitation, and I'm very happy to give a seminar here. So
it's my pleasure, sir.
Yeah. So this is the title of my seminar today. And actually, maybe I can start from the thing that I gave a webinar last year in July. The Pretam invited me it's one of the webinars last year. And at that time, the title of my talk was like the first 1 second of the early universe and the physics beyond the standard model. By the way, can you see the pointer?
Mouse? Yes, sir. We can see. See.
Yeah. So at that time, it was a bit like a colloquium style. So I discussed generic things on the physics beyond the standard model, our universe, and so on. So I talked many things on the small part of kind of very broad topics. But this time, I would like to give a more seminar-like talk based on one specific research work based on this, my own work 2 years ago or 3 years ago about the neutron star and its implication for the physics beyond the standard model called Axiom. So I like to talk about this thing, the neutron star implication on the Axiom. But for that, I think I need some to explain some backgrounds on this physics. So there are two backgrounds. One is the particle physics. So here probably I repeat small part of the previous talk about the standard model of particle physics and a little bit on beyond the standard model, and then talk about the main topic, Axiom. This is a new particle, new hypothetical particle, which is motivated by some hints. And then I also talk about a little bit about backgrounds on the neutron star physics, and specifically one specific neutron star called Cas-A neutron star and its temperature. So probably I think most of today's talk I spend on these two backgrounds on this my own work, and then briefly talk about what we did in the talk. Okay, will that be okay? I think, yeah. Okay.
Yes, sir.
Yeah. Okay, then let's start from this part. This is a little bit the same as the previous one, but anyway, I talk about it. So yeah, this is about the elementary particle physics. So as you know, the atom is made of electron nucleus and nucleus made of proton neutron. And proton neutrons are composed of quarks. And there are two kinds of quarks, up quark and down quark. So up quark has spin charge 2/3, and down quark has charge -1/3. So depending on the combination, it can give a +1 charge or 0 charge for the proton and neutron. And then electron is also elementary particle, as far as we know. And like up-down quark, quarks form a pair. Electron also has a pair with neutrino, and they are called leptons. So we can say the elementary particles are quarks and leptons at this stage. And somehow we know that there are 3 generations of quarks and leptons. So like up-down quark, there are charmed strange quark, top-bottom quark. So they are basically the same as this up-down quark, charge +2/3 and -1/3, +2/3, -1/3, but they have different masses. Also, like electron, there's a particle called muon and tauon. They also have the same charge electron as the electron, but the mass is different. Also, there are 3 kinds of neutrinos. Actually, these 3 neutrinos mix each other, and the mass eigenstates are different, but I don't talk about it today. And also, there are 3 kinds of gauge bosons. They are also elementary particles, and those gauge bosons mediate the 3 forces of the standard model of particle physics. One is the strong interaction mediated by the gluon, and electromagnetic interaction mediated by the photon, and then weak interaction mediated by weak bosons or WZ bosons. And then there is a Higgs boson, which was discovered in 2012. So all these particles are already discovered and theoretically very well understood. So this is the standard model of particle physics. So that's the all matter content of the complete theory as far as we know today. So this standard model, so there are many particles in this theory, is described in terms of quantum field theory. So if you know the quantum mechanics, it says that the Planck's constant is non-zero. So in the limit of Planck constant to be 0, it's reduced to the classical mechanics. And also, maybe you already learned the special relativity, that the speed of light is not infinity, but it's finite. So if you take the speed of light to be infinity, it recovers Newton mechanics. So if you combine these two, both finite Planck constant and a finite speed of light, then you have to go to the quantum field theory. And then, so yeah, standard model is described in that quantum field theory. And in quantum field theory, the properties and interactions of particles are written in terms of Lagrangian. So it's the same as the quantum mechanics, but more precisely, it's written in terms of Lagrangian density. But basically, it's the same as quantum mechanics. It's one of the quantum mechanics. So for instance, the electron is coupled to the photon. So this describes various things like Compton scattering or E plus E minus annihilation and so on. Many interactions are described by this interaction, and it's written like this equation. This is Lagrangian, one of the Lagrangian terms. And this psi is electron or positron. This A mu is a photon, and this is a coupling strength. So anyway, the interactions and various properties are all written in this Lagrangian density. That's the basic ingredients of the quantum field theory. So for the standard model, the Lagrangian is written rather simply in this form. Maybe you have seen this is a T-shirt from the sun. So this simple equation can explain almost all the particle physics phenomena. It's very, very simple. More precisely, you can also write a little bit more in detail. But anyway, this kind of equation, all Lagrangian interaction. For instance, here you can see the photon coupling to quark and lepton with the coupling strength, as I said. So all other terms are for the interactions and so on. And this quantum field theory, Lagrangian, written in terms of Lagrangian, standard model Lagrangian is very, very successful. So it can explain many things in particle physics phenomena. Just to give an example, there's a quantity called electron G factor or magnetic moment. It's a electron's magnetic moment, and it's very, very well measured. Maybe I can start from this one. It's 2 times 1 plus 0.0011596521873 with this error. And then theoretically, using the quantum field theory or Lagrangian, you can also calculate this quantity, and it's 2 times 1 plus 0.001159652180252 with this error. So you see, it agrees to these two, experimental measured one and theoretical calculated, to agree very, very well up to this digit. It's, I think, 10 or more digits. So quantum field theory, it's extremely successful. So standard model in that sense is very successful. However, we believe that there must be something beyond the standard model. It's not the complete theory, but there must be something beyond it. So there are various reasons to believe that there's something beyond the standard model of particle physics. So I took some slides from the previous last year's seminar here. So there are, for instance, hints from cosmology, like matter-antimatter symmetry or dark matter, dark energy. Also, there are hints from the particle physics. And there are many candidates for the physics beyond the standard model to explain these puzzles, like grand unified theory, supersymmetry, or leptogenesis, right-hand neutrino, and so on. And there are also experimental efforts like search for proton decay, LHC, CMB, and so on. So I also should note that these things, these candidates for the physics beyond the standard model, are all still hypothetical theory. So it's not proven yet. It's not checked. So maybe it's completely different theory. So if you ask, for instance, what's the solution to the Higgs naturalness? Some theorists say it's probably supersymmetry, but some other theorists may say no, it's not supersymmetry, but something else. Or some theorists may say, oh, there's no grand unified theory, something else. So you must keep in mind that all these things can be completely different. So today I focus on one of these puzzles and one solutions to that puzzle that is called Axiom. It's not written here, but it's also related to particle physics cosmology. So that's the one background. The standard model is very successful, but we believe that something beyond should be there. Now I go to this axiom. So is that okay so far? Any question? Maybe, yeah, there's a discussion session.
Yes, so
yeah.
we can
discuss it later. Yeah.
Okay.
So now let's talk about axiom. So as I said, the standard model, SM standard model, is described in terms of the Lagrangian but there is one mysterious term called theta term. So this is the term. So there is some coefficient. This is essentially just constant. There is a parameter called theta, and it can take a value between 0 and 2 pi, any value. And it's a coefficient of some gluon interaction or gluon term. Gluon is the gauge boson that mediates a strong interaction between the quarks. And what is mysterious is that theoretically this theta can take any value between 0 and 2 pi. It's just a free parameter. So it may be, I don't know, 0 0.1, 0 0.3, or 1, square root of 2, anything. However, experimentally, it is observed to be 0, almost 0, essentially 0. There is a constraint on this theta, and from neutron electron dipole moment measurement, it's known to be less than 10 to minus 10. So this theta should be 0 or as small as 10 to minus 10. This is very, very strange. So the problem is why this free parameter theta is so small. It's called strong CP problem. Maybe you think that some of you may think that, okay, it's experimentally observed to be 0. Why don't you just take 0? 0 is allowed. So what's the problem here? So more precisely speaking, it's a bit more, there is something more. So the theta term is a combination of two completely independent terms originally. So there's a parameter coming from the gluon coupling, like this one. And there's also a term or phase of the quark mass matrix. So these two parameters are originally completely independent in the Lagrangian. So I don't write this quark mass matrix term, but there's something, another term, which is in general complex. And because of the complex numbers, it has a phase. And these two terms should cancel each other to be almost 0, 10 to minus 10. And moreover, this quark mass matrix is known to be complex from other observations, from the CP violation. So naively, it should be like this 10, up to 10 digits, these two terms should cancel. For instance, if one of them is order 1, it should be like 1.0000001 minus 1.00000 to make it as small as 10 to minus 10. So this is very unnatural, or in other words, it's fine-tuned. So that's why people think this is a serious problem. It's hard to believe that some theory, somehow free parameters are chosen in such a way that the subtraction makes it so small. So it would be nice if there's a more natural explanation why this theta term is so small. So this is a strong CP problem, why this theta is so small. And the most attractive or most widely studied solution to this problem is the axiom or Pichet mechanism. So I skipped the detail, but essentially this mechanism replaces the theta term by a field or by a new particle called axiom. So this theta is now replaced with this axiom field. There is a coefficient Fa because A is a dimensional full parameter. Anyway, it's replaced by this new field. So it's now not a parameter, but a dynamical field. Then this axiom will have a potential like this, periodic potential. And in such a way, automatically, that at the minimum of the potential, the theta is 0. So therefore, now you don't have to tune the parameter by hand. Just to promote it to the axiom field, then it automatically, without tuning, make at the bottom of the potential, this theta to be 0. Or vacuum expectation value of the A is 0 in such a way that theta, effective theta term is 0. So this is very attractive solution to this strong CP problem. Moreover, this axion field or axion particle can be the dark matter of the universe. So again, I skipped the detail, but coherent oscillation of this field, it's a bit different from particle picture, but anyway, this axion can play the role of the dark matter in our universe. And there are many experimental efforts to find this axion dark matter in the universe. Okay, so bottom line is the axion is attractive candidate for the physics beyond the standard model. So it's very widely studied and both theoretically and experimentally. So in this slide, I want to talk about the axion's properties. And essentially, this only one parameter, Fa. So Fa is the parameter here in the denominator of the axion field. So the axion coupling to gluon is given by Fa. Axion coupling to photon is given by an Fa. Axion coupling to quarks and leptons also given in terms of Fa. There are some coefficients here, order 1 coefficients depending on the details of the model, but roughly speaking, it's all 1 over Fa. Also, the axion's mass is determined by the Fa, by this equation, but if you plug in this up quark, down quark mass, pion mass, and so on, at the end, it's just the Fa. So axion mass is also inversely proportional to the Fa. So very roughly speaking, up to some detailed structure of the models. So these are some models of the axions, but roughly speaking, all parameters are determined by Fa. So this Fa is the most important parameter for this axion theory. And as I said, this is an attractive scenario. So it's extensively studied both theoretically and experimentally, and there are many studies. So, for instance, these experimental experiments searching for the axion dark matter. Also, there are various constraints from the stellar coolings. One of them I will talk about later. Also, from cosmology, dark matter should not too much. Dark matter abundance should not be too much. So these constraints now leave the window for this Fa. So this Fa should be between 10 to 8 GeV and 10 to 12 GeV. So this axis is the Fa from 1 GeV to 10 to 18 GeV. And as I said, axion mass is inversely proportional to Fa. So axion mass increases in this way from 10 to minus 11 electron volt to 10 to 6 electron volt. And the window is here. So these blue regions are excluded. So the allowed region is it's here. So between 10 to 8 and 10 to 12 GeV. So what we did in our work is to give another independent bound on this Fa from the neutron star. That is as strong as this 10 to 8 GeV. So we could obtain a lower bound on Fa independently of the previous works. Okay, so now I finished this part, axion, the particle physics part. So essentially, the main message is axion is a well-motivated candidate for the physics beyond the standard model. Now I changed completely the topic and now talk about the neutron star. So it's a bit different topic, but it becomes important later. So I spent some time on this part, neutron star and Cas A neutron star. So neutron star is a a compact star. Its mass is about almost as heavy as solar mass. So it somehow in between 1 and 2 solar mass. Heaviest one actually found very recently, not that recently, 1.5 years ago. The mass is measured to be 2.14 solar mass. This is the heaviest neutron star found so far. The radius is also known. It's about 10 kilometers. So if I put the neutron star in your university, it's like this. It's 10 kilometers here. This one is the Pabna University, right? I searched it in Google. So if you know the mass and radius, then you can also calculate the density, the mass divided by the volume of this ball. Then it's 7 times 10 to 14 gram per centimeter cubic. It's as heavy, as dense as the nuclear density. It's almost the nuclear density, but slightly heavier, factor 2 denser. So it's like a huge nuclei. You can regard it as a huge nucleus. And of course, neutron star is mostly composed of neutrons, but there are some fractions of protons and electrons and even muons. It's not 100% neutrons, but partially there are protons and electrons. And those fermions, neutrons, protons, and electrons, are all degenerate. I don't know if you already learned this Fermi surface and Pauli blocking things, but this is momentum, neutron momentum, and so up to certain value of the neutron momentum, the states are completely filled, occupied. So you cannot put more particle here because it's a fermion, Pauli blocked. And then above this surface, Fermi momentum surface, there's almost nothing. So in other words, the temperature, that is the width of this transition rate, is much smaller than the Fermi momentum. So basically, you can regard it's almost zero temperature gas. Also, proton electrons are also Fermi degenerate. And observationally, most of the neutron stars are found as pulsars, and more than 2,000 pulsars or neutron stars have been found so far. So there's a nice catalog. You can go to this web page and check the properties of these pulsars. One of the most famous one is this crab pulsar. Okay, so this is the properties of the neutron star. So we know the mass, the radius, and there are many neutron stars observed. Now I want to talk about one very specific neutron star that is called Cas-A neutron star. First, I want to start from this Cas-A. So Cassiopeia A is a supernova remnant. So, you know, at the end of the star evolution, the supernova, some of them make the supernova, and in the sky, people found various supernova remnants. So the remnants of the supernova. And so this Cassiopeia A is one of these supernova remnants found. We know the position of this Cassiopeia A very well. It's in the, as the name says, it's constellation Cassiopeia. This is the Cassiopeia constellation, and this supernova remnant, it's here. It's the red circle. So we know the position in the sky, position of this supernova remnant very well, so very precisely. Also, we know the distance to that object within this era. So we know, say, three-dimensional position of this guy, supernova remnant. Cassiopeia A. So also, interestingly, we know when this explosion or this supernova happened. Of course, it takes many years that light of the supernova remnant supernova reached the Earth, but the time that the light reached the Earth is about 300 years ago. So this supernova remnant is as old as 300 years. So this is 300 years old object. So there are two interesting suggestions. One is the remnant expansion. So just by looking at this supernova remnant, by extrapolating or interpolating that the speed of this dust and so on, you can go back in time and estimate when this remnant started. Go back to the point. So in this way, you can estimate when this explosion happened, and it's estimated to be 1681. So sometime in 17th century, within this era. And another interesting thing is that this guy, John Flamsteed, found a star in the sky on this day, August 16th of 1680. So he recorded, I found some star in sky, and it's called 3 Cassiopeia or 3rd Cassiopeia. I don't know how to call it. It's here. But somehow this star found by Flamsteed was missed after that. So it disappeared. He found the star, but it's no longer there. So maybe he just found he saw the explosion itself. And of course, after the explosion, the star goes away. So nobody could see that star afterwards. So this is the supernova remnant, which is now observed. And this is the Cassiopeia A found by this Flamsteed. And if you compare, yeah, it's the same position. This is Cassiopeia constellation. So it's here and here. So maybe he really found supernova. Now that's the supernova remnant. Now I talk about neutron star. So in 1999, Chandra satellite, this one, found a point source at the center of this Cas A supernova remnant. So this is a supernova remnant. And at the very center, the satellite found a point source of X-ray. An X-ray spectrum is consistent with the thermal emission of a neutron star with a carbon atmosphere. So it's consistent with the neutron star mass, 1.4 solar mass, and also consistent with the neutron star radius. It's almost 10 kilometers. It's most likely really it found a neutron star at the center. And of course, the supernova theory also predicts after the supernova explosion, at the center of the supernova, either black hole or neutron star is formed. So it's of course natural that neutron star is there at the center of the supernova remnants. And furthermore, its temperature is observed, and not just observed, but the cooling is observed. This is very special for the Cas A neutron star. So this is a plot. Can you see this? I don't know if you can see these numbers. So it's starting from year 2000, and it's year 2010. So during these 10 years, the temperature, surface temperature of this neutron star has been observed, and you can see it decreases with time. So it's really cooling in real time. And this is the only isolated neutron star whose cooling has been observed in real time. So this is why this specific neutron star is interesting. And temperature decreases by a few percent in 10 years. It starts from 2.12 to 2.04. So it changes by, yeah, a few percent in 10 years. So this paper, it was found by this paper, ended in 2010, but there is a more recent data. I thought I replaced it, but okay, here. So more recent data in 2019. So it goes now. It continues 18 years. It's still decreasing. So there are two different plots, but its temperature is decreasing. So this is very interesting. Neutron star cooling. So now I spent a little bit time on the neutron star cooling theoretical aspect. Maybe this is a bit difficult, but let me try. So this is an equation that describes the evolution of the neutron star temperature. So this capital T is the temperature, and small t is the time. So the change of the temperature with respect to time. And the C is the heat capacity. So the change of the thermal energy with respect to the temperature. Then in the right-hand side, you see just from the dimensional argument, there must be something change of the energy with respect to time. So basically, this equation says the temperature decreases by the energy loss of the neutron star. There are two sources of energy loss. One is the neutrino emission. It's here. So neutrino can be emitted from anywhere in the neutron star. And another contribution is photon emission. It's only from the surface, so it's 4 pi r squared surface area times Stefan Boltzmann constant times temperature to the force. But in the case of Cas A neutron star, which is as old as 300 years old, so it's very young neutron star compared to the others. So in such a young neutron star, it's known that the photon luminosity is much smaller than neutrino luminosity. So basically, you can only consider this neutrino emission, and you can forget about the photon emission. This photon emission becomes important only very old neutron stars, as old as millions years old neutron stars. So you can forget about this photon. So now the equation becomes very simple. Just neutrino emission determines the temperature evolution. So there are 4 contributions of the neutrino emission. Let's go step by step. So first of all, this is called direct Uruka process. This is essentially the beta decay. So if you know the beta decay, it's a decay of the neutron to proton to electron and neutrino. And inside a neutron star, you can also think of backward interaction. The proton and electron can go back to neutron, emitting neutrino. So by this pair of interaction, you emit 2 neutrinos and can lose the energy. So this would be the dominant contribution to the neutrino emission. However, it requires the momentum conservation. And this momentum conservation does not work because of this Fermi-degenerate distribution. Maybe it's difficult. Maybe it's hard to imagine, but only small fraction of the states around this Fermi momentum is available for this kind of interaction. Above this Fermi momentum, there is no such particle, and much below this Fermi surface, they cannot be used for the interaction because they are essentially Pauli blocked. So only around here is available for the interaction, and just by you check the number, then this interaction is not allowed. The momentum is not conserved. So this does not happen. And actually, even if it happens, it cannot explain the data. So we can ignore this direct Urka process, at least for this Cas A neutron star. Then the most important process is now what is called modified Urka. So it's basically the same as Urka process, direct Urka, neutron to proton, electron, neutrino, but now you add one more particle in the initial and final states. So either neutron or proton is added in this initial and final states. Now it becomes 2 to 4 or 3 to 3, more complicated interaction. Therefore, you have more momentum to allow a momentum conservation. So even if the allowed phase space is small, it's now allowed. But instead of that, now this process is very much suppressed. So there are 5 particles which are in Fermi degenerate state. So neutron, proton, electron, and one more proton or neutron in initial and final states. So in total, you have 5 particles which are degenerate. So each of these guys give a temperature to power 1. Then in addition, there's a neutrino emission, which is also suppressed. So in total, its luminosity, the energy loss per time is proportional to the temperature to the 8th power. That's the modified Urka process. And similarly, here now, in this case, the neutron proton is coupled to double boson, and electron neutrino is emitted. But you can also think of a neutron coupled to Z boson and neutrino pair is emitted. But essentially, with the same reason, it's also suppressed by T to the 8th power with a slightly small coefficient. So anyway, these two processes, modified Urka and Bremsstrahlung, the luminosity, the neutrino emission energy loss, is proportional to T to 8th power. So for the moment, I neglect this one, PBF, and consider these two processes. Then, as I said, the luminosity is proportional to the T to the 8th power, and heat capacity is also calculated to be then in its single power of T. Then you can easily calculate, I think, this kind of equation. Temperature derivative with respect to time is proportional to the T to the 7th power. It's very simple differential equation. Then the solution is the temperature is time to the minus 1/6. Now for the Cas A neutron star observation, it's as old as 300 years, and the observation took place about 10 years. So that within this 10 years observation, the change of the temperature should be like this. I just expand this equation with a small delta t. Then in 10 years, it should change, the temperature should change only 0.5% just by this simple equation. And it's a bit complicated, but now the surface temperature, this is the internal temperature of the neutron star, and there's a somewhat conversion from the internal temperature to the surface temperature with this power. But this 0.5% change of the internal temperature is converted to the even smaller change, like 0.3% of the surface temperature. So theoretically, the surface temperature should change only 0.3% within 10 years. But as I said, observationally, the temperature change was about a few percent. So in 10 years, the observation tells us that the neutron star was, this Cas A neutron star was cooled by a few percent. So observation the temperature is cooling much faster than the theory. It's rapid cooling compared to the theory. So that was somewhat very interesting for this gas neutron star. Now comes this PBF process. This is actually related to the Cooper pairing. So if you have heard of superconductivity in the condensed matter, so in the condensed matter physics, the electron pair, two electrons can form a Cooper pair, and it can cause a superconductivity, and it gives various interesting physics in condensed matter physics. Now, in the neutron star, inside the neutron star, it's so dense that neutron pair or proton pair can form, like electron pair in condensed matter. And below some critical temperature, it becomes superconductivity or superfluidity. So there is an energy gap so there's no state in this energy gap, and the proton pair and neutron pairs are formed. And then this modified local processes in Bremsstrahlungs are even more suppressed. But on the other hand, there's a new process called Cooper pair breaking information, PBF, is enhanced. So yeah, I skipped the detail, but below the critical temperature, after the phase transition, it triggers a sudden cooling of the temperature or sudden emission of the neutrino pair by this pair formation and breaking. So sometimes neutron pair is formed and it's formed, broken, and in this process, you can emit the neutrino pair, and it can cause energy loss very efficiently. Therefore, efficient energy loss causes a rapid change of the temperature. So these people calculated the temperature change, taking into account this Cooper pairing or superfluidity inside a neutron star, and found that it can nicely explain the observation. Like this blue one is a theory, this red one is the observation, by somehow adjusting the parameters of the superfluidity gap parameter. So theoretically, this neutron pairing gap, especially this triplet gap, is very uncertain. There are many models. This is a Fermi momentum. This is a gap, energy gap. So various models. So in some sense, you can fit the data by using this uncertainty. So you can adjust this height and width of this energy gap such that it can go through this data. So to summarize, that this Cas-A neutron star can be explained within the standard neutron star cooling theory, and superfluidity and superconductivity to proton play key roles. So it's published in 2011, 10 years ago, by these people, and it says this is the first direct evidence that superfluidity and superconductivity occur at supernuclear densities within the neutron stars. Another paper, almost at the same time, says this is the serious evidence for nuclear superfluidity in neutron star cores. And so it even says evidence superfluidity in the core. Okay, so that is the Cas-A neutron star. Now, in 5 minutes, finally, I talk about my own work. So the Axiom physics, motivated by the strong CP problem in standard model, and neutron star physics, especially the Cas-A neutron star cooling. So we combine these two things to give a new bound on the axiom. So what we did is very simple. So as I said, this neutron star cooling is governed by this equation, essentially neutrino emission. However, if there is a new particle, hypothetical particle axion, there can be a new energy loss from the axion emission. So since we know the axion coupling to the proton and neutron depending on this order 1 coefficient. So this is FA, very important parameter FA. We can calculate the axion emission rate from the neutron star. And similarly to the neutrino emission, there's a somehow counterpart for the axion Bremsstrahlung, also neutrino PBF, correspondingly axion PBF. And these rates are already calculated by these people some time ago. So basically what we did is there's actually a nice public code, NSQ, that calculates this neutron temperature change a bit more detail. So we added axion emission part in that code, public code, taking into account these parameters, model parameters, and then see what happened to the temperature. So this is one of the typical example. This is the time, age of the neutron star from 10 years and 100 years, 300 years. This is luminosity of the from the neutron star. So this black line, for instance, is the neutrino emission. So you see there's a jump here. The neutrino luminosity is rapidly increasing here. That corresponds to phase transition. But now these various lines are corresponding to the axion emission, and you see in this parameter case, axion luminosity or energy loss by the axion can be larger than the neutrino emission. So it can cool the neutron star more than neutrino in some parameter space. So this is the temperature against the age of the neutron star with this green dots at observation. So if there is no axion, the best fit line goes this black solid line. So it can somehow fit the data. It's not as good as the previous paper, but it's because of our fitting. It goes like this way. Now, if the FA, the axion interaction is 10 to 9 GeV, it can still fit the data. So this blue dotted line can still fit the data like this one. However, if you make the FA to 4 times 10 to 8 GeV, this blue solid line, then the best fit line, even if it's best fit line, it doesn't fit the data well. It's very poor fit. So we can say this 4 times 10 to 8 GeV is not good. It's excluded. The axion interaction is too strong, or in other words, neutron star is too much cooled by the axion compared to the observation. So in this way, we could obtain a constraint on this axion parameter. And in this specific model case, we obtain this 5 times 10 GeV, and it's as strong as the best bound obtained so far. Okay, so to summarize the main part, there's a rapid cooling of the Cas A neutron star observed, and it's theoretically very well explained in the standard neutron star theory without particle physics beyond the standard model. So you don't have to put anything. It's just standard theory can explain it. However, if there is a new particle like axion, it modifies the cooling, and therefore there is a constraint on such a possibility. And we obtained a new bound on this axion decay constant, which is as strong as the bound known so far. And our result is also cited by this particle data group. This is how to say summary of all constraint experiments and so on for the particles. It's updated every year, and our result is cited also here. So there are also related papers here obtained similar results. Anyway, so that's the end of my talk.
Thank you, sir, for your wonderful presentation. So if you allow, we can start discussion session. We have got some question.
Yeah.
So the first question, so what is the coupling strength Maybe you have already explained in your
Coupling strength
strength.
of what it is.
Yeah. So
Uh, okay, so first one, I think first I explain it in terms of maybe electron.
yeah, you have already explained.
Okay, let's share the screen again. Share. It's shared. Okay,
Yeah, yeah, you can see. Just
yeah. So this is the coupling of the electron. So it's like a charge. So maybe yeah, the if you have two particles with plus charge and minus charge, it feels attractive force. And if it's one and one, the attractive force is say one. And if it's two and minus two, the attractive force is four, right? It's proportional to the charge. And you can regard this coupling strength is like a charge. So it describes the strength of this force.
yeah, thanks, sir. We have another question. So, does Axiom help us to understand the dark matter problem?
Axiom.
Yeah, Axiom.
Yeah, it does. Yeah, I don't have a specific slide for that. Yeah, but yes, it can be the dominant component of the dark matter. Uh, yeah, so it's again determined by this FA. So if FA is around 10 to 12 GeV, depending on this order one parameter, this omega h squared is it's a quantity to how much dark matter is there, the density of dark matter, and its observation it's 0.2. So depending on the parameter, it can explain the whole dark matter in the universe. Yeah.
So, sir, this may be the last question. So,
Mm.
does axons emit from supernova explosion? So, you
Yeah,
have
yeah.
explained from Neutron star. So,
That's
similar from supernova explosion. Okay.
that's a very good question. And actually, can I share just one
Yeah.
paper? Recently, we wrote a paper on that.
So,
So
have we developed any detector for detecting these axons? Or is it similar to a neutrino detector?
yeah, that's the thing. So
Yeah.
the not yet, but it's even more difficult than neutrino from the supernova. But the supernova axion can be emitted from the supernova. So if the supernova happens in nearby our Earth,
Yes.
in principle, we can see the axion. So these
Uh,
are actually detector try to see the axion from the sun. This is already there; it exists. So we propose to put another detector in the other side because it cannot. It's energetically it's different from the sun. When the supernova occurs, you can change the direction in such a way that axion now can be observed by the same experimental setup. And of course, you have to know when the supernova explosion happens in advance to do such an experiment. But there's a nice framework called SNOOS that by neutrino, by pre-supernova neutrino, you can predict the when supernova happens like a few hours before the explosion or a few days before the explosion. Then you can point this specific detector to the supernova and just wait for the axiom.
you said for your wonderful presentation and discussion session, sir. So I think the students have learned a lot of things about this new particle, and hopefully some of our students may join in this new field in near future. So I would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation for the second time. It's our great opportunity for us also, including our student and teacher, to learn a lot of things from you. So thanks again, and it's our honor actually to host you in our International Physics webinar. And hopefully in near future we'll arrange another webinar with you for student. So and hopefully
right.
after the COVID, I'll definitely invite you for our for a face-to-face session and to visit our beautiful country, Bangladesh.
Yeah.
Bye for today, and thanks again.
Yeah. Thank you.
Yeah, bye.